All right, so in section 2.6, we're asked to put two functions together. You should have already seen addition, subtraction, multiplication, and division. Composition is a little bit different because one function happens before the other one. That's a little bit different than if you're just adding two functions or multiplying two functions. Okay, so we're just run through a few examples here. Some where you actually plug in a number, and then a little bit more general x values. Okay, so this little open circle represents composition. It's probably most important and most helpful if you realize that that's notation we use to say f of, and again that's what we usually do, f of x, f of 2, f of 6, but in this case we're doing f of g of 2. Okay, so again that circle, the composition circle means f of g of 2. Well, we always know in math, right, we do the inner part first, so we figure out, well, what's g of 2? Well, g is just the squaring function, so we square the 2 to get a 4. Okay. Now we know that 4 is supposed to be plugged into f. Remember, the f function just doubles the input and then subtracts 1. So you double 4 to be 8, subtract 1 to get 7. Okay, but again, we had to get through the g function first completely to get the output from g becomes the input for f. Okay. The second one will show you that composition is not commutative. So if I do g of f of 2, right, again, that means I start inside here and figure out, well, what's f of 2? Well, again, remember, try to think of these functions in words. So the f function just doubles the input and then subtracts 1. So you double the 2 to get 4, subtract 1 to get 3. And now you plug 3 into g, which again is just the squaring function, so you get 9. Okay, so again, just kind of notice right away that when you reverse the order of composition, it's likely you'll get different outputs. It's not a commutative property. Okay, so we just see this again for negative 3. So f of g of negative 3. Again, start on the inside. What's g of negative 3? Remember, g is just the squaring function, so you square the negative 3 to get 9. F function doubles and subtracts 1. So double the 9 to get 18, subtract to get 17. And then again, if we reverse it, we would expect a different output. So first we do f of negative 3, double, subtract 1, so we get negative 7. And then square, we get 49. Okay. And the next couple ones, we're just inputting an x. So again, this is more algebra or just symbolic manipulation here. So we put in a symbol, we expect to get a symbol out, not number to number. But again, it's just f of g of x. And again, it doesn't matter if we plugged in 2, we plug in negative 3, or we plug in x. The g function is the squaring function, so it's going to square that input. What does the f function do? It always doubles the input and subtracts 1. Okay, so this can't really be cleaned up, so we just leave it as that algebraic expression, 2x squared minus 1. Okay. Similarly here, we have g of f of x. It doesn't matter what goes into f. F takes whatever the input is, doubles it, and subtracts 1. So I would double the input x and subtract 1. Okay. G, again, is just the squaring function. So I take the whole input and square it. So we could write it like that. You could also write it, if you want to square it out, as 4x squared minus 4x plus 1. Okay, it doesn't matter to me generally which way you leave that. All right, and then just a couple more here just to show you can compose a function with itself. So we have f of 2. Well, again, just remember the f function doubles and subtracts 1. So we double 2 to get 4, subtract 1 to get 3. And then you plug 3 in again, double it to get 6, subtract 1, you get 5. Okay. G of 3. Again, g is the squaring function, so whatever goes in gets squared. So plug the 3 into g, you get 9. Plug the 9 into g, you get 81. Sorry. So that's the composition of two functions. Okay, and that's what we do most of the time. The next couple examples just give you an idea about how this works backwards. And this is useful. The next couple ideas are really a lead into calculus. So we see it a little bit here. Could appear on the test, but mostly we use it to get us ready for calculus. Okay, and the idea is when you look at these two functions, h1 and h2, they're both essentially two-step functions. Okay, in number 3 for h sub 2, it's a little bit obvious. First you do the parentheses, then you square it. Okay, here it's a little bit more subtle, but clearly first you would do x plus 3, and then you would square root it. So again, it's sort of a two-step function. First, you'll add 3 to the input, then square root that result. Here, whatever the input is, you'll do 3 times it minus 5, and then square the result. So again, when it's two steps like that, you think about breaking it down into this composition of two functions, okay? So again, if we want h1 of x, which we're given to be x square root of x plus 3, to be written as f of g of x, well again, remember, you want to think of it as this way, f of g of x. So g represents the inside function. G represents what you do first. So in our problem, what we would do first is add 3 to the input. So that's going to be our g function. Okay. Then what do we want the f function to do? Now again, keep in mind this has already occurred. What do we want the f to do? Then we just want to square root it. Okay, and it's a little tricky with the notation, but we're going to have to square root the result. So again, what we want to do is find our f and g. So again, g is the inside function. We want to add 3. So we call that the x plus 3 function. Remember, f, we want to square root. So again, it's just the square root function. Okay, and so if we check here, if we do f of g of x, remember the g function adds 3, and then the f will just square root that result. Okay, so it's a little tricky because people want to put the plus 3 here, but the idea is we're trying to separate it into two pieces. So let the inside function in our case be g, and then at the end I just want to square root it. So it's just the square root function. Okay. Similarly for here, again, we want to do this part first, so this part will be our g function, and then f just needs to square it. G will take care of the inside, f just needs to square it. So again, in this case, h2 of x equal to 3x minus 5, quantity squared. The inside part here is going to be the g part. The squaring part is going to be the f. Okay, because again, keep in mind we want g, we want this to equal g, f of g of x, which again means g of x is first. Okay, so the first thing we want is the g of x to be 3x minus 5, and then when we take that result, we want to square it. So again, we just write the squaring function. So this is here really the check. Plug it in. What does g do? It takes 3 times it minus 5. What does f do? F just squares it. And that's exactly what we want it to be. Okay. So again, we use this a little bit more often in calculus. Composition is putting the two together. In these two examples, it's just an idea, give you an idea about how to pull it back apart, back into the two separate functions. Again, the reason you'd want to do this appears a little bit more often in calculus. Okay. All right, one more calculus idea that uses composition, and a few things we've learned so far is this difference quotient. This is really a calculation for slope. So if we have a point on our graph, which we've seen many times as x comma f of x, sometimes we want to move a little bit. So we just add h to x, well, and then this becomes another nearby point. And this is simply calculating the slope between those 2 points. Okay, so we subtracted the y's. When you subtract the x parts, you get x plus h minus the x, so you're just left with h. So we use this slope calculation a lot. Okay, we just want to make sure that we can calculate this and clean it up a little bit, okay, for different functions. Okay, so the first one, we have f of x should be 2x plus 1. And again, it's kind of remember, it's, I think, always a good idea, instead of thinking of it as f of x equal to 2x plus 1, or use words. So whatever the input is, you're going to double it and add 1. That's what the f function does. It takes any input, doubles it, and adds 1, no matter what the input is. Okay. So again, we're just working on this whole fraction. Well, most of this is pretty straightforward, except for this little piece. So I'm going to do this off to the side. So this f of x plus h is the only one that can be somewhat of a challenge. So again, I'm just going to work that off to the side. But again, f is not a complicated function. We just said it takes any input, doubles it, and adds 1. So it's going to double this and add 1. Now, I can distribute if I want to, which I will, but there's not much else I can do to clean it up. Okay, but that's the first piece of the puzzle here. So my slope, m, is this huge fraction. The first piece is this, minus f of x, and then I'll have my h on bottom. Okay, so f of x plus h is 2x plus 2h plus 1, minus f of x, which is how it's given to me. Okay, that's it. We just want to clean it up a little bit. So we clean up, get rid of these parentheses on top. So I distribute that minus, so it becomes minus 2x minus 1. And keep in mind we still have our h in our denominator. Couple things drop out here. We have positive 2x, negative 2x. We have this plus 1 minus 1. And so our m looks like just 2h over h, okay? And then that will cancel, the h's will drop out, and you'll get m equal to 2. Now keep in mind through this whole problem, h should not be 0, because that's in our denominator. But if you clean it up completely, you would get m equal to 2. Okay. All right. Keep in mind, by the way, since we were working with a linear, right, you know that to be a line of slope 2, and you're just sort of showing that here. Okay. So same thing here. This is a little bit more complicated because we have this 3x squared minus 5. But again, keep in mind, try to say it in words. What does our g function do? It takes the input, squares it, multiplies it by 3, and then subtracts 5. Okay. So again, we're asked to make this calculation, the difference quotient. So we're going to take g of x plus h minus g of x all over h. Okay. Most of that's straightforward. Again, I'm just going to work out this g of x plus h off to the side. Okay. All right, but again, what does g do? It takes the input and squares it, multiplies it by 3, and then subtracts 5. I can leave it like that since I'm going to have to clean up anyway. I'm going to clean up a little bit over here. So I'll square this out. That's x squared. Remember, inner and out are both xh, so that'd be 2xh plus h squared. We still have our minus 5. And I'll distribute to 3, so we get 3x squared plus 6xh plus 3h squared minus 5. And again, no like terms to combine, so we'll just leave it like that. Okay. All right, so we come over here. M equals, and again, it's this big difference quotient. We have the first piece, which we just calculated off to the side. We have g of x written already for us over the h. Okay, so first I type in this, or write in this, 3x squared plus 6xh plus 3h squared minus 5. G of x is the 3x squared minus 5 all over h. So it's sort of our answer. We're just expected to clean it up a little bit. So again, I just basically remove parentheses. So the first one, there's coefficient of 1 in front of it, so nothing happens to this guy. Minus, this will always be minus. That's part of the definition or the formula for the difference quotient. So it's a minus 3x squared plus 5. Keep in mind, just defined to be an h in bottom. You would expect a few terms to drop out. So we have the plus 3x squared minus 3x squared. We have the minus 5 plus 5. So we only have a couple terms left on top, 6xh and 3h squared. And then we could see we could do some factoring. Okay, so again, we just clean this up a little bit more. We could take out a 3h, and leaves us with 2x plus h over h. And again, those will cancel. And so I'm left with 2x plus h. And again, it's just a nice habit to say, remember, h can never be 0 in this problem since it's sitting in our denominator.